notes of the year. Inference for two-way tables. What happens if we want to compare more than one variable or more than one population? Here's what we're going to do. We're going to use either a chi-squared test for homogeneity, or we're going to use a chi-squared test for independence. One of those two will be used. How do I know when to use which one? Anybody know what homo means? Same. Anyone knows what geneity means? Like your genes, it's like your makeup, it's like how you are made, right? So a chi-square test for homogeneity is going to be when you want to see if two different populations are made up the same or not, all right? So this is when you have two or more populations or treatments. Chi-square test for homogeneity is going to be when you have two or more populations or treatments and you're trying to see if they are distributed the same or if they're distributed differently. A chi-square test for independence. You have one population, but you have two variables, and you're trying to see, are the variables associated? So that is when you're trying to test whether or not these variables are associated or independent of each other. Okay, so that's the chi-square test for independence. That you only have one population, but you'll be notating two different variables. All right, here's the good news, you guys. They work exactly the same in regards to the calculator. Okay, so you're really just learning one more inference procedure in your calculator. But it works for both of them, independence and homogeneity. All right, how will the observed counts be reported to you? It will be reported to you in a two-way table. This is going to be true for homogeneity and independence. You will get a two-way table similar to this one. How do you get the expected counts? All right, so we've got this two-way table, observed counts. If you need to get the expected counts, I'm going to tell you how to do it by hand, but just know your calculator will help you out. So what you would do, let's say, for instance, I want to know what is the expected number. Did I skip something?
Yes. You said you confused me.
Hey, I'm sorry. Let me go back, please. So here's the example that's going to take us through these notes. So market research suspects that background music may affect the mood and buying behavior of customers. One study in a Mediterranean restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. 3 different treatments. So we're going to look at these as 3 different populations. Okay, so there's 3 different things going on here. And we are trying to see, under each condition, the researchers recorded the number of customers who ordered French, Italian, or other entrees. So here is our data. So we have 3 different types of music. Those are the treatments. And we're trying to look at, is the distribution of entree ordered the same or different in each of these distributions or treatments? So a chi-square test for homogeneity would be the one we would use here. It's homogeneity because we have 3 treatments and we have 1 variable, which is the entree. The treatments is the music. So whatever music is playing, that's the treatment. The entree that they are ordering, that's the variable that we're notating. All right, your null hypothesis for a homogeneity test is that there is no difference in the distribution of that categorical variable for several populations or treatments. The alternative, there is a difference between the distribution of the categorical variables. So what would the hypothesis be for this particular problem? So the state, we will test at alpha equals, what would alpha equal? 0.05. The null hypothesis, there is no difference in the distribution of entree ordered for, this is something, we're actually writing in context of the problem. There is no difference in the distribution of entree ordered for each music type. And what would be the alternative? There is a difference, blah, 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 in the distribution of entree ordered for each music type. There either is a difference or there's not a difference. The null hypothesis, we assume everything is distributed the same. The alternative, we think there's something going on here. Look at your data real quick. With no music playing, we had 30 people order French food, 11 people order Italian, and 43 order other entrees. With French music playing, we had 39 order French food, 1 order Italian, and 35 order other. Does there look like there's a difference there?
Yeah.
Okay. With Italian music playing, 30 people ordered French food, 19 ordered Italian, and 35 ordered other. Does there look like a difference there? Y'all know what the question is, though, right? Is the difference due to sampling variability, or did the music really make a difference? That's what we're trying to figure out. Okay, cool. So how do you get your expected count? Man, this keeps skipping. How do you get your observed counts? Your observed counts are going to be the two-way table. Now, the expected counts. In order to get the expected counts, there's a couple ways you can do this. So we know that 30 people ordered French food when there was no music playing, but how many would we expect to order French food when no music is playing in this sample of 243? Here's how you can get the expected counts. You can take the row total times the column total and divide by the table total. The row total times the column total divided by the table total. That's how you can get the expected count. So, for the French food with no music playing, the row total would be 99. The column total would be 84, and the table total would be 243. So what would be the expected number of French entrees ordered when no music is playing? Do that math right there. Right now. Plug this in. What'd you get? 34.22? Ladies and gentlemen, we would expect 34.22 people to order French food when no music is playing. We actually observed 30. Is there a difference?
Yes.
Yes. All right, good. Now, you guys, to get the expected counts for all of the other categories, we would have to do this 8 more times with all of those different ones. Doesn't that sound fun? Or we could use our calculator. Wouldn't you rather do it this way?
Yeah.
All right, cool. All right, we'll keep going then. I'll show you how to do it in your calculator in just a few minutes. All right, conditions. What do you think the 3 conditions are that you're going to use? Random, independent, large count. Why are we not using normal?
Because it's not a normal distribution.
What's not a normal distribution?
Chi-squared.
Chi-squared is not a normal distribution. Random. We have an SRS, independent, 10 times, okay, all right. Large count. All expected counts are greater than or equal to 5. We have to verify that all the expected counts are greater than or equal to 5. There is one of our categories where an observed count is not greater than 5. It is the Italian food with French music playing. There was only one person that got Italian food when French music was playing. That is totally fine. That's the observed count. We just need to make sure the expected count is greater than or equal to 5. Once we get the expected counts, we will use the chi-squared statistic. We will get the sum of all observed minus expected squared divided by expected. But you guys, we will have to do that over all the cells, not including the totals. So if we did this by hand, we would have to do all of the expected counts, 9 of those. Then we would have to do 9 of these with the observed and the expected. Squared divided by expected. So much. Okay? Here are the observed and the expected counts. We can see right there under the expected counts, they are in fact all greater than or equal to 5, so we're good to go. For the French entree with no music, there were 30 that were observed, and there were 34.22 that were expected. So the chi-squared contribution would be observed minus expected squared divided by expected. That would be 30 minus 34.22 squared divided by 34.22. And we would get that number, and that would be the contribution from that one cell. But then we would have to do that 8 more times. Don't you think it's time to just use our calculator?
Yeah.
All right, cool. So we're going to use our calculator to find the chi-squared test statistic. It will add up all of those values for us, and then it will actually do our expected counts as well. Okay? So here we go. Do any of you remember Algebra 2?
No.
Barely. Do any of you remember the matrix?
Oh, yes.
We are going to use a matrix. Yes, you guys are all about to take the red pill, okay? It's matrix time. So here's what you need to do. Second, and the X-1 button on your calculator will get you into the matrix. You need to go second and the X-1 button. It literally says the word matrix above that button. I know you don't want to be in the matrix, but I want you to be in the matrix with me. Come on, it's fun here. All right. I need you guys to go over to edit. Go over to edit. And you're going to go to number 1, which has matrix A.
Where's X minus 1?
X minus 1 is like 4 below the second button. If you go I think it's like 4 down.
Oh.
All right. Has everybody found the matrix? And has everybody found matrix A, and you are on the edit matrix A? Okay. The first thing you have to do is input the matrix size. All right. So you need to input matrix size. What size is our entree music matrix? Not including totals. 3 by 3. So all you have to do is you type in 3, enter, 3, enter, and you should get a matrix with a bunch of zeros, with 9 zeros. Did everybody get that? Perfect. Now you need to input the data, the observed data. Okay? So now you're going to input observed data. My biggest suggestion when you're inputting the observed data is just definitely on the very last entry, make sure you hit enter. Because otherwise, it'll stay 0. Right, Alex?
Yep. That's what you said.
Yep, that's what I said. All right, does everybody have their matrix plugged in? Yeah? Hope, Morgan, yeah?
Yeah.
Got your matrix in? All right. Stat. Test. C for chi-square test. Stat. Test. C. Chi-square test. Stat test C. Chi-square test.
Were we supposed to put something in B?
No. I love that you said, what about the B, right? So look, you see where it says observed it has the little matrix A bracket? Expected, it has the matrix B bracket. But did we put anything in matrix B?
No.
Guess what? Your calculator is going to put it there for you.
Is that the point? So that's how we find this. Because this is how we get to us. Okay.
Okay, time out. Calm down. We're getting there. All right, kids. Does your calculator ask you for anything other than observed and expected?
The color.
It doesn't matter which color it is. Is that it, right? Hit calculate, please. Hit calculate. What do you guys see?
10, 18.
You got the chi-squared. You got the p-value. What else did it give you? Degrees of freedom. That was it, right?
Yeah.
All right, now, here we go. Yes. Did you put in the data under matrix A?
No.
Don't touch anything yet.
I think I did something wrong. Can you fix it?
Stat, test,
I went and downloaded
C.
He's trying to accelerate brain. Yeah. I think I'm losing too many brain cells.
So, yes, so your matrix. You didn't put your data in.
Oh, that's how you do it. Because I tried putting in the number.
3 by 3.
Thank you, Miss Lee.
Yes. All right. All right, kids. Stat, test, chi-squared test, chi-squared value, your p-value, your degrees of freedom. Okay. Fambro, are you with me? Hayden, are you with me? All right. Here we go. I'm going to tell you how degrees of freedom are for here in just a second.
No way you just asked that.
But first,
No way you just asked that.
stat. I'm just kidding. Don't do that. Go back to the matrix, everybody. Shh. Back to the matrix. Hey, go back to the matrix.
Second X minus 1.
Second x minus 1.
And then click enter.
Now, ladies and gentlemen, I need you to go over to edit, but this time go to the B matrix.
Well, looky there.
Expected values are listed. So, while you might not get the expected values in the problem, you can go here and get the expected values. Pretty cool, huh?
Is it like the plus version? He likes like the normal one.
All right. Got it? All right, cool. Hey, did anybody write down the chi-square test statistic that you saw just a minute ago?
18.2.
Oh, no. What if you didn't?
18.28.
Then what can you do if you didn't write it down?
Go back.
You can go back to stat test C. Stat test C. And 18 point what? 2.8? All right. Austin asked, how do you get degrees of freedom for a two-way table?
It's in there.
Row minus 1 times column minus 1. Row minus 1 times column minus 1. It's your tip. Row minus 1 times column minus 1.
Buy me something with it.
Okay, got it.
Buy me a Hot Wheel with it.
All right, row minus 1 times column minus 1. There were 3 rows. There were 3 columns. So anybody know what 2 times 2 is? 4, which is exactly what the degrees of freedom were.
No way.
I know, right? And what was our p-value?
Actually, plus that.
0, 0 what?
Go up.
Shut up. Bro, shut up.
Up.
Dude, Hayden, I'm trying to learn. We're tired of you. How does that equal 4?
2 times 2?
Oh, I thought it said 2.2.
I thought it was.
Wait, how do you get p-value? Was that listed?
2 times 2?
What look like?
The p-value was under stat test C.
Yeah.
Okay.
I thought you just pulled that up. Not a...
Uh-huh. There you go. Out of my back pocket.
Yep.
All right. Oh no, we have to interpret the p-value.
Oh no.
Assuming the distribution of entree ordered based on music playing, assuming the distributions of entree ordered based on music playing are the same, there is a 0.0012 chance of getting sample values as extreme or more extreme than the ones we got just by chance. Period. Assuming the distributions of entree ordered based on music playing are the same, there is a 0.0012 chance of getting sample values as extreme or more extreme than the ones we got just by chance. Ladies and gentlemen, there is a 0.0012 chance that this distribution happened because of sampling variability. That means there is a 0.9988 chance that there was an actual difference to be seen. Hence why we are now going to conclude this. P-value equals 0.0012. That is less than alpha, which was 0.05. And so therefore we are going to reject this hoe. There is convincing evidence that the distribution of entree ordered based on based on music playing is different. We have convincing evidence that the distribution of entree ordered based on music playing is different. It is different. Yes, basically what this is saying is that music does in fact influence your choice of food. Did you know that? Any questions, comments, concerns, thoughts, feelings? We're not done. We still almost done. We're not there yet. We're gonna get to the bottom of this page. Woo! Everybody good? Got it? I'm waiting for Morgan. Okay, she's got it. All right. Part C. Please remember, We can also find the p-value if we are given the chi-squared test statistic by using chi-squared CDF. Remember, chi-squared value. Let's say we got, what was our chi-squared value? 11 point what? 18, I mean. What's 18? 18 point what? 2.8? Remember, you can use chi-squared CDF under second vars. Everybody go second vars, chi-squared CDF. Chi-squared CDF, please. Your lower boundary would be the chi-squared value. What would your upper boundary be? And what would your degrees of freedom be? Degrees of freedom?
4.
4. Everybody go to second vars, chi-squared CDF. Second vars, chi-squared CDF. Plug this stuff in.
Who's that for?
This has nothing to do with the matrix, children.
That was a little bit.
Chi-squared CDF.
I'm actually sick of being in the matrix. I'm actually sick of hearing you.
Just like use it.
What'd you get? Yeah, your lower is 18.28. Your upper is infinity. Your degrees of freedom is 4.
And second bar is what? Normal CDF?
Chi-squared CDF, sis.
Oh, wait, where is that?
8.
Oh,
It's like 8.
I did 7.
Hey, you guys, what did you get?
I know.
0.0011? It's almost like that's the same as the p-value.
It's close.
It's literally the same.
It's close.
It's the same.
I mean, it's probably.
All right, guys, what questions do you have about that? Okay, I have really good news for you. We're not done.
Oh, okay. Then it's not good. Okay.
Chi-squared test for independence. Everything works exactly the same. There is
Can we not finish this tomorrow?
no association versus there is an association. That is the only thing that's different. Everything else is the same.
Who was the call for?